Good morning or good afternoon. My name is Dario Dainelli, and I'd like to thank you, the organizer, for inviting me in this conference. Unfortunately, I will not be able to attend because at the time you are looking at this presentation, I will be in a flight. You have my email address, so any question you might have after the speech, you can email to me. Let me share my screen. A minute. Okay, I hope you can see my screen now. The title of my presentation is about sustainability, and particularly for recycled plastics. So the point that I'd like to cover is how to ensure consumer safety while using plastic coming from recycling processes, and particularly for post-consumer recycling processes. I would try to answer some questions during this presentation. What kind of food safety and quality risks might be identified with recycling for polymers, in particular mechanical recycling, which is the most widespread process for polymer recycling, how this risk can be managed through legal mechanisms, and how these legal mechanisms are in place in different jurisdictions across the world, what kind of difference are between the approaches used in the United States and Europe concerning standards for safety assessment and protocols, and how are the recycling system validated by using these systems. But first and foremost, circular economy. So the transition towards a circular economy or a more sustainable economy has become a priority in many countries, certainly in North America and in Europe, but increasingly also in other countries in Asia, like in China, and in Africa, Latin America, etc. So circular economy has now become the predominant business model in many fields: transportation, building, automotive, etc. Plastics have been subject of an important action plan known in Europe as the Plastic Strategy in 2019. This is a strategy which aims at transforming the way the plastic products are designed, are produced, used, and recycled in the European Union. Plastics are certainly an important material in our economy and in daily lives. However, they might have negative effects on the environment if they are not properly managed at the end of life, at the end of their service life. The Plastic Strategy aims at making recycling profitable for businesses through rules on packaging to improve recyclability and increase the demand for recycled plastics content, as well as improving separate collection, so curbside collection of plastic waste. Developed countries have adopted circular economy principle as a part of their growth strategies. And this model not only implies a lower impact on the environment and ultimately on environmental health, but also includes many other advantages: boosting recycling, preventing the loss of valuable materials, creating jobs, and also creating economic growth, adopting new business models and building knowledge that might eventually be translated into other technology fields. Developing eco-design for food contact packaging materials, but not exclusively in this field, and promoting industrial symbiosis, for example, through integrated collection, sorting, recycling, and use systems. It is widely recognized that the consumption of resources of our planet, of course, cannot be indefinite, and that the economic growth that so far has been made possible with the intensive use of oil, mineral, water, forest, other resources that cannot be replaced is now close to downturn. And circularity in the economic growth is already a reality and will certainly become more and more important, a strong driver for the future economy. It is impressive how things have changed rapidly in the last decade, when public opinion's awareness has enormously increased towards environmental themes, and support to environmental activists has literally boomed. Organizations such as Greenpeace, WWF, the Ellen MacArthur Foundations, and other organizations now have a wide support and are often partnering with governmental organizations for the implementation of strong initiatives with very high impact on business and on society at large. Many policies fostering circularity of plastics have been adopted on a global basis. For example, the European Union set challenging targets for plastics, 25% recycling for total plastics by 2025 and for 55% by 2030, and incorporation of recycled PET in beverage bottles of 25% by 2025 and 30% by 2030. In addition, it is requested to collect 77% of PET bottles by 2025 and 90% by 2029. It is obvious that such a high collection rate must correspond to an equal increase in the capacity of the PET recycling, or the plastic recycling in general, using packaging materials. For example, for polyester, the current share of rPET over the total PET in Europe is about 1/3, and almost all of it used in packaging materials. This figure accounts for a shortage of rPET in the European market, and of course, a boosting of price. It is expected that the policies adopted will provide industry with increased capacity of rPET. In the US, the initiatives are more taken at the state level rather than federal level. However, there is an increased number of states, such as California and New Jersey, the Northeast Coalition, that have adopted measures that promote directly or indirectly recycling of plastics, and in particular PET bottles. Sustainability is a key word, and all these initiatives push the economy to become more sustainable, or in other words, to decouple the economic growth from the consumption of resources. There is no doubt that plastic recycling represents a highly sustainable industry. However, there are several challenges for presence of contaminants in the post-consumer plastic waste stream, which makes the post-consumer waste recycling more critical, particularly when using food contact application. There are main contaminants that originate from the packaged food itself, such as limonene from beverages, oils, fats, and aromas, which might be absorbed in the plastic. There are also incidental contamination for misuse, for example, storage of solvents or fuels or other liquids into the bottle. Some non-food contact containers might also be source of contaminants, lindane from shampoos, methyl salicylate from cosmetics and other solvents, and degradation products and additives. Degradation products typical from PETs is acetaldehyde, but also you might have oligomers in all kinds of plastics, particularly polyolefins. There might be residues from chemicals used in the process, such as alkali from washing and removal of labels, and other plastics which might taint the stream that is to be recycled. For example, in the PET recycling, presence of PVC, polyolefins caps, and other components such as adhesive, they might be, and they are in fact detrimental to the quality of the stream. PET is certainly one of the best suited polymers for recycling. And this slide shows why PT is so best suited. It is not indeed the only one, but it is intrinsically shows physical chemical properties that allows easier and faster cleaning from any potential contaminants that might have polluted the bottle during the post-consumer phase. PT has a high melting temperature, over 250 degrees, which means that one can heat it up and volatiles are easily stripped, so that can be found in the final recycled plastics. On the other hand, as temperatures raises to strip out volatiles, impurities and contaminants might decompose and might cause problems relative to spots, colors, and burns, and other kind of undesired contamination. That's why high purity is needed in the input stream, and the best collection is, and the best is the quality of the final RPT. PT, unlike polyolefins, is produced via polycondensation. That means that it can be depolymerized by temperature and also by solvents, and subsequently it can be repolymerized. This leads to another form of recycling, which is not completely discussed into this presentation, which is chemical recycling, which is equally safe, mainly, but less frequent because of less economically sound. So the PT can be modulated in terms of molecular weight in the polymerization phase, giving enough time the polymer and the polymerization to proceed in the so-called solid phase polymerization, and this leads to an increase of the molecular weight, and then to better volatilization of the contaminants and possible decomposition products. The molecular weight is very important for processability. In fact, it is well known that for the PT bottles, this requires the PT quality requires a high molecular weight than the grades used in other applications such as fabrics or textiles. The diffusion coefficient, which corresponds to the rate at which a certain molecule travels in the polymer matrix, can provide an explanation of the PT behavior. PT has a much lower diffusion coefficient compared to, for example, polyolefins. That means that the contamination takes place at a lower rate and will remain more superficial compared to other polymers. And this makes the decontaminations easier. Especially this is true in dry condition, where the plasticization effects caused by moisture are reduced. When it comes to food contact material, the general safety requirements associated to food contact materials are reported in this slide, in particular in the top left. So packaging shall not endanger the consumer through product adulteration due to chemical migration from the packaging to the food, and shall not impart the taste on the taste and the smell of the product that is contained in it. The statement is taken from the European Regulation 1935/2004, which is setting the general requirements for all food contact materials. And in fact, with minimum differences, this statement is adopted virtually in all countries having regulations on food contact. For RPT, all existing regulatory systems aims at qualifying the suitability of processes to clean up the flakes and obtain food-grade PT pellets. These systems are focused on the process and not on the product, because the process shall be demonstrated suitable no matter the quality of the input material. Obviously, the quality of the input material is important, but within a certain range of contamination, the efficiency of the process in the removal of the contamination is what the regulatory agencies have interest in determining. A scheme for the core decontamination process is also reported here in the bottom of the slide, which is in fact very general, but common to all decontamination technologies. you can see how the decontamination takes place in several different points on the line, in melt, and also at the level of the production of the pellet. Now the question that you might have is, okay, but how do I prove that the process has the capability to clean up the chemical contamination, regardless of the chemical nature and the quantity of the substance that might have entered into the polymer, and no matter of their concentration? This is in fact the question that stands at the core of the overall decontamination process, and even more of the core of the application that recycling companies has to file to either the European Food Safety Agency or to FDA for the risk assessment of their process. The answer resides in the so-called challenge test, which is a test that demonstrates that the measures and to demonstrate and measure the cleaning ability of the process. The challenge test consists in spiking clean virgin material with known amount of specific substances that are referred as surrogate contaminant in a quantity which is typically ranges between 500 to 1,000 ppm. Then the process of the spiked materials are put into the process themselves, and one goes to analyze the level of spiked substances in the output material. This quantity in the output material determines the residue concentration. That is a function of the molecular weight and the volatility of the surrogate contaminants. And controlling this residue concentration will allow control and optimization of the process conditions. And finally, the level of these spiked substances shows the ability of the process to reduce contamination. And this is the parameter used by risk assessor to define restrictions, potential restrictions on the use of the material. So these surrogate contaminants are selected in order to simulate the behavior of any other contaminant, representing the range of volatility, polarity, and molecular weights. So the challenge test is not fully described in literature. There are several publications, but each laboratory adopts its own different procedures. In fact, the tests are very similar to the applications addressed to EFSA or of the FDA, although there are some differences. So, but the difference between the two systems, the European and the US, is not in the test itself, but rather in how the data are used by EFSA and by FDA to determine safety of the final polymer. So the difference stands on the third point, on how the different agencies use the outcomes of the challenge test to determine the process capability. But despite these differences, we can say that the level of safety determination achieved by these two agencies are practically the same. There are, as I said, two main systems of risk assessment and authorization of recycled plastics. The US and Europe, the European. US FDA approves recycling plants since 1991 and have approved now, well, 181 grades. There's probably a little bit more now. This has been done in 2021. The US system is conceived to address all kinds of plastics, although PET is the majority, but also includes polymer other than PET, such as high-density polyethylene and in some cases polystyrene. And for this reason, it can be considered a bit more flexible than the European system. The EU system is in principle also made for all plastics, but in practice, the way risk assessment is made by EFSA is applicable only to PET. And in fact, with very few exceptions, all these 240 recycling plants assessed by EFSA are 99% plants dealing with rPET. Well, we don't have a lot of time to go into the details of the risk assessment procedures, but if you are interested, you can email to me and we can discuss offline. So other systems in different jurisdictions are modeled after these two systems. Australia and New Zealand accept RPT authorized by EFSA or FDA. Mexico, the Mercosur countries have the same approach, and recently Pakistan has adopted the same decision. Other systems such as Canada and Japan are equivalent to the FDA, and Thailand also is in the process of expanding its food control legislation and adopt a procedure using the same FDA approach. In the next slide, I show here the comparison between the American and the European authorization system. Well, authorization is probably not the right word, certainly the assessment system. FDA issues a letter of no objection upon application of an applicant, of course, whilst the European Union has a more complex legislation, which is going to change because a new draft for the legislation has been presented by the European Commission in December 2021. And in the European system, the European Food Safety Authority makes a risk assessment, and this risk assessment has to be adopted by the Commission and translated into a risk management action known as Commission decision. But these are only administrative details. Do not be misled by the fact that the US has a voluntary system. So the system in the US is voluntary, in fact. But in fact, even the FDA pre-market notifications for virgin polymers is not mandatory in FDA. To understand this, we should go into the legal construction of the US law, but as a takeaway message, you should notice that all operators who want to produce or use recycled plastics in the US actually go to FDA and obtain a letter of no objection. The EU system is more formal and might be more bureaucratic, requiring by law quality control and quality assurance, stipulating audits by the European national authorities of each member country, and requires a minimum purity of the collected PET stream of 95% food grade. So maximum of non-food grade, which must be contained into the input stream, should not exceed 5%. So the EU approach consists the general strategy of a regulation called 282/2008. This is pretty old. It's about 14 years ago. And as I said, this law is going to change. The new draft is being presented, and within 2022, the new draft will most likely be adopted. These systems enable direct food contact use of post-consumer plastics. The recycled plastics should comply with the regulations for virgin food contact plastics, which is the regulation called 10/2011. Recycled plastics in the inner layer of the ABA structure are excluded from the legislation. Although this is under discussion, it is not clear at this point in time whether this will last also in the new system. As I said, the process of recycling is subject to the EFSA opinion and the Commission authorization. So we have more than 200 opinions delivered, almost all related to PET. This slide is a very, very short presentation of how EFSA approaches the risk assessment for recycled plastics. Actually, EFSA, the European Food Safety Agency, starts from a reference contamination level of flakes, which is considered a maximum of 3 milligrams per kilo PET. And this has been measured back in the 90s with a project which examined the contamination of several thousands of different bottles all across the different countries. So starting from this point, the EFSA, through the results of the challenge test, they can calculate the efficiency of decontamination. And through this number, which is the efficiency of decontamination, and using this formula, they came to a value which is called residue concentration, CRES, residue concentration. This residue concentration is then compared with a model concentration, which is calculated starting from the maximum tolerable intake of 0.025 micrograms per kilo body weight per day, which is corresponding to the concentration, maximum concentration for CMR substances. And by using this number and by applying migration modeling, they came to another number which is called model concentration. When the model concentration is lower than the residue concentration, then EFSA consider absence of safety concern. If not, if this is reversed, then there are safety concern. As you can see here, the starting point is PT. So everything else which is different from PT would have problems of being assessed by EFSA because of lack of any system to calculate the residue concentration. Therefore, this system suits almost entirely to PT. I, of course, will not go into the detail here, but since no maximum concentration exists for other polymers such as HDPE, polypropylene, etc., then the calculation is not possible. And therefore, application which entails the usage of polyethylene, recycled polyethylene, they are either failing or just put on hold. This is, for example, the case of HD application received by EFSA in 2015 concerning, again, polyethylene, high-density polyethylene used in dairy product, milk product in the United Kingdom. So in 2015, EFSA received 2 applications from UK relative to the recycling of HDPE for different uses. You see here, without getting into the details, how let's say, deep was the analysis to select the field of application, the scope of application for this recycled polyethylene. However, the challenge test which was produced, it was executed. It was actually executed with conventional methods for PT in absence of other methods, which ended up into a concentration of the residue higher than the model concentration. And therefore, the conclusion from EFSA was that this method is unsuitable to determine safety. As a consequence, these 2 recycling processes for HDPE have been put on hold in 2015, and they are still on hold. The US approach, as I said, it's different, all right? As I said, it's voluntary. So US, unlike Europe, takes into consideration different type of recycling. The recycling of pre-consumer scraps, which is considered of low hazard, considered recycling anyway. So it is not master or not subject of letter of no objection. So pre-consumer scrap are easily and freely recycled. The so-called physical reprocessing, which corresponds to secondary recycling, called also secondary recycling, which is the one dealing with mechanical recycling, grinding, melting, reforming. And this is also has to be demonstrated as safe by means of a challenge test. And third is the chemical reprocessing or tertiary recycling, which is a regeneration of purified starting materials, also considered of no concern. So eventually, the system in place for in the US is again dealing only, the system of letter of no objection is only dealing with physical reprocessing or secondary recycling. FDA again approves recycling process since a long time, and there is a system which is quite similar to the one in Europe. So recyclers and sensor, they have to submit an application describing the input material, the process of decontamination, result of the challenge test, and so on and so forth. And they have to demonstrate that the maximum concentration does not exceed the maximum acceptable level of contaminants. FDA issues a letter of no objection, and when anything happens in the technology, so if a different technology is put on the market, then it requires a separate approval. And the new challenge test is to be produced. So the main difference from Europe, as I said, is into the assessment system. Here, you have a starting point consisting on the maximum acceptable level of contaminants in the polymer, which corresponds to the estimated daily intake equal to 1.5 microns per person per day. It depends on the type of polymer itself. So the density, the thickness, and the quantity of this particular polymer which would be in contact with the daily diet. So here you have a calculation which is made by different polymers. What is changing is the density of the polymer, and what is changing is also the so-called consumption factors, or the fraction of any specific polymer which will enter in contact with the average daily diet. That means that there's nothing such as residue contamination here. So you only have a maximum residue which can be calculated by different polymers. So you see a maximum residue on polyester corresponding to 220 microns per kilo, of polystyrene of 300 microns per kilo, of polyolefins 320 microns per kilo, and of PVC. And in principle, you can make the same calculation for any type of polymers, which means that this system is much easier and much more easily applied to polymers different from polyester. For the US systems, there's nothing such as the 5% maximum contamination by non-food grade polymer. You can actually use both food grades and non-food grade feedstock, and the same standards of purity will apply. It would include also non-food in the feedstock, then the level of contamination in the challenge test, it is recommended to be increased. So to conclude my presentation, we can say that collected post-consumer plastics can be safely recycled into another food content use. The food grade RPT or polyolefins or recycled polyolefins might be produced from validated decontamination processes, and the validation is made through a challenge test based on a well-established principle of safety. The criteria adopted by US and Europe are different, but they are equally protective. And in principle, recycling process technologies that are accepted by the US FDA or by the European Food Safety Agency can also be accepted elsewhere. The opinions issued by FDA or EFSA can also be regarded as valid for compliance purposes. And the gap in the EU risk assessment process in general makes recycled polyolefins more difficult to be authorized, while the US FDA already includes assessment system, which is valid for both RPT and recycled polyolefins. As I said, the system in Europe is under revision. Actually, the discussion is there for quite a long time. So we are now close to a change, to a modification, and in a few months, we will be able to see how the new system will work. Hopefully, by opening the doors for quicker innovation and also making polymers other than polyester more easy to be accepted and utilized. And this is my last slide. Stop the presentation here. Thank you very much for your attention.